20 minutes or 10 minutes. All right, so let's hope it stays. All right, so it's currently recording. Yeah, so let's go ahead and bring in some of the libraries. We will need ONNX this time, so I will go ahead and install those this time around. Let's load the environment in our Colab. So you can see the same Torch NN, Torch Functional, Torch Optim. And these are the same little libraries that can train something as powerful as ChatGPT, right? So this is, totally doable. So we are going to need these now because I'll show you how to do the ONNX. It uses JavaScript essentially, so it's a little bit similar to what you are familiar with. All right, so pip install ONNX ML tools. Make sure we install that. Okay, so that, yeah, ONNX tools is done. And now we're going to do ONNX runtime, and they're just basically like different versions of it, right? So ONNX runtime is currently, as of the last time I checked, the state of the art, if you will, the newest version, the new reframing. All these libraries are constantly being like reframed every few years. But this is very powerful library. You can deploy many types. I know students that have deployed even really large models. So here's the thing. So deploying a large model is possible with ONNX. The limitation is where you host it. Do you see that? So one thing that you should know about GitHub pages is that it has a maximum limit for files that you can load there, and I think it's 25 megabytes. So any file above that, I think you have to get like a special plan, and then it's 100. But you can also just host your model somewhere else, right? So for instance, a good place could be like the Hugging Face hub, just huggingface.co, I think. And that's a place where you can host your model, and then you can still access it from pages, right? So there's workarounds. All right, so just keep that in mind. So for your homework, don't build such a big model. All right. Yeah, so so we've installed the libraries, and now, these have been already available. Now I'm going to do this one. Notice this time around, it's exactly the same ones, tensor dataset data loader, but now, because it's a regression problem, the metrics are no longer going to be precision, recall, and F-measure, right? Now we're going to use the R-square, which you've already used in your WECA assignments and things like that when you learn the pipeline. So essentially, the library just changed to that one for the metrics. And then this time around, let's see if XGBoost is available also, because I want to have it available. And you can see, so XGBoost has its own library. Again, it's a decision tree type of an algorithm, like random forest, those kinds. But it's a super, you can consider it like a super decision tree, right? And this library also is very efficient. It has been created for performance. Whenever you go to Kaggle, which I'm sure you guys are familiar, or if you ever go to a hackathon or you ever compete somewhere, and you get a data set that is a regression type data set with not a lot of data, I highly recommend bringing XGBoost into that competition. Let other people, you can try the neural network, but don't neglect this one because it's extremely powerful for this type of problem. Always wins in competition. All right, now we're going to bring in our libraries for ONNX also. All right, and what's great about this is the pipeline is still the same, right? PyTorch just holds the model. All right, so all we have to do is generate the file. That's it. We're going to dump out the file from ONNX, right? So we invoke ONNX runtime, ONNX ML tools, SK, and also you can see SKL2 ONNX. So this is because you can also deploy your XGBoost model, and have it on your website. Do you guys see that? So this ONNX framework doesn't just support PyTorch, it'll support other ones as well. All right, so that's what's really great about it. All right, and now we just get back into the pipeline that you guys are familiar with. So we've got the parameters here, batch size 16, learning rate 0.005, 100 epochs, and the epsilon, so we don't have any division by zero numbers. Okay, we're going to read in our data, just like before, the wine quality data set. But now we're not going to treat it as a classification data set. We're just going to treat it as a, regression data set. So I need to load, of course, I forgot to load Google Drive. And we need to find the full path of the wine quality data set. Okay, here we are. So my drive, let's copy the path, Control V. All right, so we can go ahead and, all right, and there we are. So we have our data set once again. Yeah, we've read it, so we can view it. It'll be the same one. Okay, and you can see it right there. So now the key thing is we're going to treat these as regression values, so we don't have to create a set of classes. Remember that we had 7 classes before, so the output vector was vector of 7. This is going to be now just, so that meant that the output layer was 7 neurons. Now it's just going to be essentially 1 neuron. So that's the difference, right? So that we will see. Okay, so I've got my data. I'm going to skip this part because we've already done it. You can look at the correlation matrix, etc., just to get a look at the data. But here I will skip to the part where we now go from pandas to NumPy. All right, so we've converted the data into NumPy. And now we can go ahead and slice the data into our X and our Y, right? So the last column now is going to be the Y, and the first 11 columns are going to be the X. And there you go. You can see it's the exact same pipeline. So you can contrast between classification and regression. Here, before, we were changing this. So this is one of the differences, right? Before, we were always changing Y to integer. Do you guys remember that? We would make it int because it was classes. But now it's a regression data set. So we don't necessarily, we can leave it as regression data, right? So you can produce 23.7 as a value. That's okay. So we're not going to change it. It's the same 5,000 or so samples, so we are going to take the randomization. Remember, this is key for the project. I'll repeat this again. When you present your results of because remember, you have to present both phase 1 and phase 2. It'll be like a little hackathon type of competition. So you guys need to show your results out of 10, right? 10 runs. So that's what, and it has to be randomized so that we see all the values and we take an average of all your either ours, in your case, it'll be F1 scores. All right, so that's the random seed. And please stop me if you have questions. We do the split again, train test split. Same as before, 20% for tests, so about 1,000 test samples. Here it's definitely a good idea to print the shapes just to get a feel for where we are. Okay. All right, you can see 3,918, 11, 3,918, 1. So we've got the same split as before, different randomization though. The data type, so here, notice that this changes, right? Before we were using ints here in the Ys, notice that difference. Now we're just gonna leave these we're changing all of them to float 32, from float 64. This is just quantization so that we don't run into issues with memory, etc. Okay, so now they should all be float 32, and then now they're ready to be converted into PyTorch tensors. Okay, so PyTorch tensors, so that's done. All right, then here I'm going to standardize the data. Okay, so X means and deviations. I'm going to get the means and the standard deviation so I can later standardize the data in the model. So as you can see, all of this is the pre-processing pipeline, and it's pretty much the same. And now we can go ahead, and here's the approach to convert our data into a tensor data set and a tensor data loader. You can see that here this is going to be a little bit different. Okay, in the past, if you remember, I always used the data loader. Do you guys remember? So we would create the list of tuples, and then the list of tuples was added to the data loader. And that's key, right? Understanding that. However, in this example, I'm showing you a different approach. Now, what's key here is make sure to print your tensors, right? Because knowing the shape of these tensors now is key to knowing how they would be, how you would expect to load them. So let's go ahead and try this. So I'm going to grab xtrain and ytrain tr dot shape, and you can see the data is 319, 11. So your data needs to be like this. Do you guys see that? And if it's currently like this, if the shape of X is the number of samples, comma, the number of features, and it's a torch tensor, then you can take this approach of using tensor dataset. But also you have to make sure that your Y data is in the correct format. So printing the shape here is really important. So you can see it has to be 319, 1. Does this make sense, guys? So if you're using this approach, which is different from the previous approach of list of tuples, just make sure that your data has these shapes. If it does, it should load correctly. So now let's go ahead and try this out. So notice this here, we load first into the tensor data set, and then that is going to get loaded into the data loader. Okay, see it loaded fine. So that's perfect. That puts it in a format that we can use. This is we can even print it. This is going to be an object from Torch. You can see, but that's why it's key to check the shapes of the tensors in PyTorch. Okay. Otherwise, if you have some kind of a mismatch there, it's not going to like it, and it's going to give you an error. All right, now that you have your tensor data set, you can go ahead and just load into the data loader. It's the same data loader you've used before, but tensor data set is what you use here. Do you see that? We still specify the batch size to be 16 in this case, so we're going to grab batches of 16, and we shuffle so that is equal to true. All right, so now we have our tensor data set. All right, and we can proceed to the architecture. So the data is ready. So this architecture will be very similar, but also a little bit different, right? So the first thing I'm going to do, so notice I have here 3 different architectures, actually 4 different architectures that we can implement, and all of these are going to be regression. I'm going to start with the simplest one, which is the linear regression model. So what is a linear regression? Linear regression is just something that has no hidden layers, no activations, remember? So it goes back to that idea of it only can create lines that separate the data, so it has less capacity. Same idea as before. Let's get rid of these. Let's get rid of this part here. And we can see that we can create a class, we give it a name, linregnet, linear regression. we inherit NN module, just like before, right? We have our init function, and our forward function. Same thing as before. This is our constructor. We've got our x means and our x deviations for the standardization inside, which happens essentially here, okay? And in the forward, we're passing x as an input, and it's going to go through the whole neural network until it comes out. So it's the same, right? It's the same as before, but it'll have just a few subtle tweaks that have to do with the fact that this is a regression model now and not a classification. So let's now add in some of the elements. So of course we want to assign the x, just like before, our means vector of 11, right? And this one also is a vector of 11 of the standard deviations. And then we're going to use these in our formula where we have x minus mean divided by standard deviation. That is the formula that we use. Okay? So once that's defined, believe it or not, this is the whole neural network. And it's a neural network just in name because it's really not a neural network given that it doesn't have hidden layers or activation functions. It is just literally a linear function. Do you guys see this? So that's all it is. You know, we use an NN linear from 11 to 1, and that's it. That's the whole neural network. So remember, when we do these architectures, it's good to look at the diagram. So I'm going to switch over to the whiteboard. Okay. Whiteboards, new whiteboard. Remember, I'll ask questions like this on the exam. And so this one, because it's a linear regression, it only has an input layer, call it I, of what size? Dot, 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 11, right? So that's the X goes in. Usually we have hidden layers, we have activations, not here. All we have is one layer with one neuron in it. That's the output. And now this is essentially like that. Okay, so what is this one then? If we write it as a function, this is output equal X matrix multiplication W, where this is your W's, right? And then plus the bias, which is always a value you add here. Do you guys see that? So this is essentially the model we're building. We can use the same, the idea is we can still use PyTorch, right? We can still use PyTorch NN linear because it's just a matrix multiplication, but this is not a real neural network, right? I could ask you a question on the exam, like a trick question, right? Tell me something about this neural network. It's actually not a neural network, right? In the sense of the word, because it doesn't have the hidden layers and the activations, okay? But yeah, that's the simplest one that we can build. And that's how you build, because this neuron will map to any value. So any value can come out here from minus infinity to plus infinity. But the values are going to be in a range from 0 to 10 because our data is in that range, right? We've actually looked almost at the normal distribution of it, which is around 6. So the average is actually 6. Do you guys see that? And so for our regression problem like this, we just need one output. Any questions on this idea, guys? All right, so this is the linear regression, and it's a linear model. So now we need to share. Okay, we've talked about the architecture of it. Now we put it together in the forward function. Okay. So in the forward function here, this line, remember, x comes in here, and then we do x minus self x means divided by self x deviations, and that just standardizes the data. So any value now, it's going to be from -5 to +5 or so. Okay? And then now we just have to invoke NN linear. Right? So NN linear. So x goes into self, so this one. So from 11 to 1, y pred is 1, and that's it. Guess what? You just built a linear regression model from scratch. All right, so now return y pred, and there you go. That's it. All right, so we can create our architecture very easily. Notice no activation functions, no relus, none of that, right? And that's what I was saying. Once you understand this general framework, you can start building up more complex things, as we will see when we look at a CNN, and then next week when we start looking at transfer learning and adding even more powerful things to it. All right, so now that we have this, everything else is pretty easy. I'll skip these for now, and we're just going to jump to our training function. Right? Training function. Nothing changes in this function, like literally nothing, right? Same idea. We take the x from the train set, we run it through the model predicts y pred, we compare y pred to the real, and we get this like error called a loss. And then our goal is to minimize that error, the loss. Now, one thing that's key is, in classification, the loss was based on something called cross entropy. Do you guys remember that? Key question on the exam, right? Instead here, because it's a regression problem, we will look at something called MSE. Now these are, for this week and last week, my focus has been just on building the pipeline, right? So in a consistent way. So once we get through this, we'll start looking back into what cross entropy is, what MSE is. But for now, just think of it as a distance function that compares one value to the other. All right, so we do this. Now notice this part is really important. Okay. Here, our model is linregnet, right? So I'm going to have to borrow this one. Oh, I had it already, sorry. Linregnet. Right, it takes x means. Notice that's the same, so that's the model. In the optimizer, which is the thing that is calculating updating the weights and everything, calculating the sign, we map or tie the model parameters like this. That gives me the optimizer. Notice here, in the past, for classification, this was cross entropy. Now this is MSE loss. Loss Fn. We pass all the parameters to the training loop, and now we train our model. And you can see 24 is the first loss, but now it's gone to 0.62, right? So that's what we want. We want the values to go down. Then sometimes it can jump, but it's still not 24 anymore, 0.39. So that's good, 32. And there you go. So it kind of hovered around 32. So that's what you want, to see the losses go down. And now finally, we're going to measure the performance of the model on the test set. So what do? You would usually put the model in inference mode or in test mode. So you take now X test, right? Not X train. We just trained on X train. Now we use X test TR. That goes into the model to produce Y pred test. Okay? Now one thing, remember, you want to make sure when you create your here actually I'm not using a data loader, that's right. So I'm not using a data loader for this analysis. I'm just giving it the whole data, X test TR. Okay? So if you want to know, what's in X test TR, you can just print the shapes. X test TR dot shape. And you can see it is 980, 11. So I'm giving it 900 samples, each vector of size 11. And now I'm going to have 980 regression values. Do you guys see that? So what do you do now? You're going to evaluate them with the R square, which is this one from sklearn. So in this example, I'm going to give it, I just invoke R square. This is at the very top when we invoke the libraries. And you need to convert them to NumPy. So I'm going to take ytesttr.numpy and also yprettest.numpy. Now, this detach, usually if you don't have that detach when you're running it on like this, it'll give you an error. And it's just the PyTorch is helping you. It wants you to detach it from the computational graph. So this is just kind of something you have to do. And there you go, 0.27.5 in this example. If you remember from R squares, you want it to go from 0 to 1. It's not necessarily the best thing, but it's, there was some learning that happened. Does that make sense, guys? So this is how you do our regression, okay? All right, so that completes the pipeline for this. Do you guys have any questions about it? Does it make sense? Hopefully it's, right? All of it, you can see that it's very similar. So let's do one more with the DLNet, and then we can move on. Now, usually when I do types of regression things, I will also just print out the values, especially if it's only like 1,000. I like to look at the predictions. It just gives me a little bit of insight. So here's a bit of code for that. Now let's try the DLNet. I'm only going to stick with one, the DLNet. We're only going to try one more. And you guys, I'm sure, I recommend as a exercise at home, try the MLP, try the F1 plus F2, try those other architectures as practice. But let's just do one deep neural network for regression. So same thing as before. Let's just remove this. Let's remove this. You can see it's the exact same architecture, a class. We're calling it DLNet. And then we have our constructor, the init class, and a forward, just like before. All right, X means and X deviations get assigned. And now we build our architecture. So I'm going to go, because these are like 2 always, right? So first one, why is this 11? You should know this by now. Why is that 11? It's the size of the input vectors, right? Don't forget that. After this, you decide the number of neurons in the next layer. So in this case, 10. And there's also going to be an activation called ReLU. All right? Then from that, and we'll draw this in a second. In the next layer, if you notice, I'm going to just need to go. I'm creating linear 2 and act 2. This one will go from 10, right? So these two have to match, to 6, right? And then I have a ReLU over here. And then the last one is called linear 3, right? Goes from 6, because this is 6, so they have to match, to 1. Why 1? Because we're only predicting one regression value. Now, you could potentially have models that are multi-input, multi-output, but this one is not like that. I'm not going to take it that far with the course, but this one is, just 1, okay? But it's possible if you want to have multi-input, multi-output, that could be 5. That's definitely doable. So that's the scenario where you're trying to predict, okay, given these values, like what's my profit margin, what's my number of customers, what's my, number of orders, something like that. So you can predict multiple values at the same time. It's a harder problem, but it's definitely possible. And sometimes it works really well. But here in our example, usually people are familiar with just multi-input, one output for regression. Okay? And that's it. Notice the hidden layers do have activation functions, but you don't necessarily need an activation or anything like that in the last layer. Notice softmax was used for classification, not for here. And that's it. These are the differences. So as you can see, they're very similar, right? You just have these little tweaks here and there between classification and regression. All right, so now that we have, in the dropout, we've talked about this, you can just use it. It helps sometimes with the training. So now that all that is put together, we can go ahead and just actually connect everything, the inference, right? So remember, x comes in, we standardize it, x minus the means divided by the deviations. Now that gives you a new standardized x. Then you add the architecture, linear 1, activation 1. So this x goes in here. It's going to be of size 11, and now it's size 10, right? And then it goes into the ReLU activation. Then we do the next layer, linear 2, act 2, activation 2. So now this x goes in to linear 2, and it gets mapped to 6. Goes through this activation to a ReLU. And now you have linear 3. And that's going to be linear 3 is where it goes from 6 to 1. So what is the size of this one, right? Remember, I like to ask questions like that. So 1611 goes in. That's the size of the batch. And this batch is going to be what? 16, 1, right? Because there's only one neuron. That neuron. All right, and now all we have to do is return ypret, and that's it. And there you go. We're done. How easy is that? Any questions? At this point, I would say you have the capacity to build any kind of classification or regression model using linear, multi-layer perceptron, and any deep neural network of more than 2 layers. Do you see that? So it's always going to be like this, and it follows a very consistent pipeline, almost a template. All right, so now that architecture is created, we just repeat this one over here. But we're going to change the model from linregnet, right, to actually use DLnet. So I instantiated the class, DLnet, and now let's go ahead and train it. And you can see that's it. Now I'm doing the same thing. I'm training my model. It's at 1.09. It's gone to 0.5. You can see, so the loss is going down. 0.29. 0.62, so it jumps around a little bit. 0.57, and we're only doing 100 epochs here. Here, maybe you should do more epochs. This is where you want to play with dropout, etc. So what do we do now? We're going to test the performance again. How do we do that? We take our test set, run it through the model. So X test goes once again through the model, and now we compare ypret test. Remember, this is a regression problem. So we want to look at the R square. .33. Our previous R square was 0.27. So a linear model was able to get 0.27. A nonlinear model, because that's a deep neural network, gets you 0.33. An improvement. What makes it linear again? Remember, having the multiple layers, having the ReLUs, and all that. The linear model does not have, see, hidden layers, only one layer, and it goes from input to output, and no activations. Does that make sense, guys? That's critical to understand. Key. All right, we're done. You are officially PyTorch masters, right? So we've completed like the first phase of all of this, like the very basic. You're at this level now, and then we have a few other levels, but you can now solve lots of problems with PyTorch, just knowing what you know now. Okay. All right. So we've evaluated performance. We've done classification and regression. So now let's see what else we want to try. So that ends this scenario. I'm going to go through, I usually print these, as I said, but if you want to print them, go ahead. I like to look at my data sometimes. I compare the real to the predicted. This was only 1,000 samples, so you really look. So for instance, I would look at this one and say, oh, 498 is the prediction. The real was 5. That's pretty good. You know what I mean? That's kind of 6.14 versus 6. It's good. You know, and so that's sometimes, even though that R square is only 30.33, and you want it to be 1, and you're kind of like discouraged or whatever, but actually when you look at these values, your client, whoever you're doing this for, might say, oh, actually, yeah, this works. You know, so that's an important thing. Okay, so we made it here. All right. So now that's actually the whole pipeline, right? Now the question is, on the homework and possibly on phase 1 of the project, I haven't decided yet, I'm going to ask you to deploy the model, but for sure the last homework, which I'll assign, okay? So you'll have to deploy your model in PyTorch. So what does that mean? You already know how to deploy models partially, right? Because you did the Perceptron homework. So what you have to do is the same thing. You go to GitHub pages, right? And you're going to create an index.html, your CSS, your JavaScript, and you're going to need a file called an ONNX file that essentially is generated from here. Do you guys see that? So that's what I'm going to do here. I'm going to take the model. So the key thing to understand is this is everything, right? That's the model. You just trained it. You can now go ahead and use it. You can build a whole company around it, right? So you just need to host it somewhere on the internet. And so obviously, currently, it is like in memory, right? It's loaded in your RAM and everything in your computer. You need to like extract it from there as a file, and then that file now you can move up to your website. Do you guys see that? Does that make sense? All right. So yeah. So let's do that. So pretty easy to do. Here it is. Deploy your PyTorch model, and this is all the code that you need, nothing else. Okay? So you go over here and you do that. So what are the steps? You need to define model.eval. So that means you put the model like in inference mode, no longer in training. And that's important, like when you're using dropouts and things like that, it like stabilizes those things or turns it off. Okay? So that's why you do this step. Put it in eval. You're going to define a dummy input just to specify the size of the vector. So you're y1, 11. 1 because the model expects batches, right? That's how the model was designed. And so that you can give it just one sample. You don't have to give it multiple. And then we know that the size of the inputs is 11, right? So we've established that it is 11. So you just specify that. Do you guys understand? So that's the size of the number of features. And then you can specify these names, input names, output names. This is helpful sometimes for the JavaScript part, okay, when you retrieve things. After that, notice that you have this function called torch ONNX export. All right, and it's just a function with a few parameters. So you give it the model itself, model. You give it the dummy input that you just created. You give it a name that you're going to use. So for instance, let's say DLNet 2026, right? So this is the model that I'm creating. And so DLNet wine data. You can set this to verbose, and you add the inputs and the outputs. Now, this is the easiest approach. I will show you a second approach that has a few additional parameters, but I recommend that you look at that because sometimes what happens is in the HTML file, you're going to need a Java. You guys have taken 365, right? Or you will take it. So you know about like jQuery, right? Or you will learn about that, jQuery. So it's the same idea. You bring in these JavaScript libraries, and sometimes they have different versions, right? So you want to make sure that the JavaScript library that you're using matches the version that you're exporting. Do you guys see that? So I'll show you an example of how that works, but this is like a more generic approach. Okay? So then we just do this, run it. ONNX script. Okay. So it says it doesn't have ONNX script. Let me try it. Whoops. Okay, so I did that. All right, let's try this again. Okay, so this time it seems to yeah, I think it's actually just outputting the whole architecture. Do you see that, guys? That's kind of nice, right? So it seems to be giving you here the entire. I don't see anything that says error. It's just the exported program, the architecture of it, and so on, all the parameters. Let me just double check. I haven't seen this before. It's got warnings. Yeah, future warning, it says. Here's the model, the opt set. We'll try that in a second. Okay, so let's see. So now the thing is we exported this, right? So we have to find where it is. So if you guys see it, let me know. Okay, it's not there. It's possible I need to don't see it there. Just give me a sec here. All right, let's try this one more time. So I'm going to try to write it in that Google Drive section. Okay, Drive. So I have that. So I'm going to grab the path, see if I can put it there. All right, so here, right, export DLNet 2026, right? So hopefully it'll put it in the Google Drive section. So let me try it again. And all of this, actually, I need to run it again, unfortunately. All right, so let's try it. If you guys know of a better way, please let me know. What happened here? Oh, okay, I have to reinstall these. All right, let's do the other one. Plug this in. All right, so did it. So we should be able to run all now. Hope. Okay, so it's doing, it did all that. Loaded the data. The last dark is running linear regression right now. So let's give it a minute. Okay, so that worked. Now it's doing the DLNet part again. Any questions while it's doing this again? Nope. All right. Maybe at least we'll get better results. It was 33 was the highest we were getting. Still got 33. No, I think, yeah, 33. So we're not able to beat that. Okay, 33. The script is missing, I'm assuming. Yeah, ONNX script. Let me do that. Okay, so that's working now. And now let's run this one. This is the ONNX export. Okay, so we got a green check. So I think that's the model. So we want to confirm if it generated the file. So we would look in here, drive, my drive. Ah, there it is, right? Do you guys, maybe it was there all the time. I don't know. Do you guys see it, guys? DLNet, that's it, right? DLNet 2026 wine data ONNX. Yeah, DLNet 2026 wine data ONNX. Do you guys see it? Here it is, right? So there you go. So once you have that file, it's in your Google Drive, right? So you guys know how to use your Google Drive. You download it, and that's it. You train the model here. Now go build your website. And all you have to do is you take this file with you, okay? These files are actually pretty small, so they should be less than 25 megabytes, so you wouldn't have any issues. Does that make sense? That's how you export your model to build your own application. So now what I'm gonna, so assuming we've completed this, right? And I have my DLNet 2026 winedata.onnx, then I would now proceed to do the export part. So that's what I'm gonna talk about now. And that should be pretty straightforward, just to show you how that works. So let's go, let's leave this open, because I wanna try something. But let's go over here to the repo, right? So click on this link here for the repo. So actually, let me do this. So, because this is your. So now I'm going to talk about the homework, and I'm going to talk about the project just a little bit later on. I'll create the links. All right. So if we are in the table of contents. Table of contents. So let's let it load. Okay. So we are in this section here. Classic Iris Torch NN. So you guys click on Repo Torch, and it'll take you it's pretty slow again. What is that? So give me a second. I'm going to start sharing the screen. All right, let's share. All right, so it takes us here, right? And we're looking at this script, essentially, this script here. But down here, I provided something else that's important. So this example that we saw today, this example that we saw today is the regression, NN, and also ONNX. And I just demoed it, right? So it's what I just demoed in this code over here. However, this is more like a very simple, generic way of doing this. One problem that you might encounter is that things are always being updated. So when you build your HTML, you'll have to have a line that brings in ONNX.javascript in, right? And what might happen there is the model that you export here, the ONNX model, may be like a version 15, but you're using the JavaScript library that requires 17. So it's some kind of, it's incompatible. Do you guys see that? So that's a key thing to be aware of for this homework assignment, okay? So I provided as help this information here. This is updated deployment code and repo, okay? So you can see here it's the same approach, the same idea as before, but with a few differences, okay? It's a few differences here in the way that you do the export. For instance, you know, these three lines are still the same, but notice over here that you're setting up a version, offset version 15. Do you guys understand? So it's fine. You can use whichever one you want, but just make sure that you understand that whatever you pick here, right, defines what you're using in your website. Does that make sense, guys? All right, so key idea then. All right, so you will need to, let's say you use this code instead of this code, right? So then you need to know what ONNX versions you should use and what JavaScript you should be using. That's essentially the key thing. So what I did is I provided this example here. This example has everything that you would need, okay? So if you click on this one, right, I've provided everything in this repo as an example. So for instance, the index and index HTML and JS is your website, right? Your JavaScript, your libraries, okay? So I have tested this, and I know that the version of ONNX that I'm exporting here loads to this code over here. So I strongly recommend that you start here when you're doing your homework. Got it? This is a different example, obviously, so there's different ideas going on, but you still have a model that you train, you still export it. So I'll show you then that idea. You go to this example. There's only one Jupyter notebook here. Notice there's several ONNX files. Do you see that? Several ONNX files, because this model actually has like 6 ONNX files because I was doing multiple things, okay? But essentially, you would export one ONNX file. So go to this code as an example. And the internet has gotten super slow again. All right, so if you look in this code, you'll have to look at the libraries. It's similar but different. What matters is a model was trained here, right? You can see that. And then somewhere down here, you'll find the export code. There it is. Do you see that, guys? This is the key thing. So you would train your model, right? So it starts at this point. Model inverse is the same as model. I just renamed it. And now you use this code segment to export. But the key thing is you need to be aware of, usually that's the main problem, that op version. You know, what version you're using, 15, because that determines like the formatting that will be used by JavaScript. Okay, so you just want to make sure those two things match. That's it. So let's say, for instance, in this example, I save a model. It's called, you know, this one, inverse, or whatever it is. I think I have multiple of this in here. I might have another one. Yeah, here's another one, Lapine model forward. You see that, right? So, but what's consistent is offset version and all of that. So just be aware of this. This is key. Make sure that you are doing this correctly. All right, and then once you have that, you have this ONNX file. All right, now you're going to use this ONNX file in the website side, right? So what do you need? So we can go back to this example. So you've actually now, let's say you generated one of these files, whichever one, Lapine model forward ONNX, that's your output file. Now what you need is these two files, index HTML and index.js, and that's it. So now you just follow this approach, okay, and you build your website, just kind of like how you did the web perceptron. So for instance, in this example, notice that you bring in index.js, but you also bring, and this is key, ort.min.js. This is the library that supports the ONNX file, okay? So you'll need to have these. And of course, these can change depending on which version you're using. So that's how you need to have a compatibility between the exported file via like that op value and this file here. That's it. Once you have that, then you can build your website. You can see here this website just has a whole bunch of text boxes, buttons, all of that. You can see it here, right? That's it. Pretty straightforward. And then all the logic is happening in index.js, right? This is where your JavaScript lives, but here you have to define the library. So now we look at index.js, and this is how you run ONNX, essentially. So I have multiple functions. So each one of these functions just is a button. So essentially you just need that. For one button, one function. Got it? So how does it work? and roughly speaking, this assumed vectors of 7 also, not vectors of 11, so you would have to change that. This is in JavaScript. You create a variable of size 7. What do you do here? You grab the values from the text boxes, so you have 7 text boxes. You load them into X. Then notice that you use the ORT library now. Do you see that? ORT, that's ONNX, it stands for ONNX runtime. And what do you do to that JavaScript vector? You convert it almost into a PyTorch type of a thing, but on JavaScript. Do you guys see that? Is this clear enough so far? Okay. So now you have a vector of 7, same idea, tensor x. And now you use this code over here to do the machine learning part, the inference, right? So you create an ORT inference session with the file that you just exported. Do you guys see that? That's your .onnx file that you just exported. And then what do? You create the session, then you run the session with what? The input tensor x. What is tensor x? This tensor x, which is made up of these x's, so the 7 values that you just entered. Got it? All right? And then once you do that, you have the results, and that's it. You're done. All you have to do from the results is you have to extract them. So results output.data. So you put that in a variable. Now it's back in JavaScript, and then you just write it out to some kind of div tag or something like that in the HTML website. Does that make sense, guys? So pretty easy, I think. Yeah. And this approach gives you the power now to deploy any powerful deep learning model from PyTorch to your website. Okay? So this is ONNX. So the key thing that might trip you up, as I said, is those versions. Be very careful there with the version. But yeah. All right. So I will give you a homework assignment on this one. This will be your last homework assignment. And essentially what you have to do is you have to use PyTorch. You have to do either a classification or a regression, and then you'll have to use ONNX, export the model, and build an application. Got it? Now, guys, you can do anything like classification, regression. You can load images if you want. All right, so there's lots of things. So I think I'm going to make the homework open-ended. So what I mean by that is you can pick any data that you want, any challenge that you want, as long as you meet the conditions, PyTorch, train it, export the ONNX file, and then show the website. Got it? And that'll be your last homework assignment. Let me give you some examples of this, right? So how it works. So for instance, you can use this one as reference if you'd like. Here's the URL, right? So this is deployed. So if I click on it, there it is. This is my application. So this is some kind of industrial thing, at a plant. And so you put in some values, about producing steel, and then it just gives you predictions. So for instance, you do that, and there you go. So with these values, it predicted these values over here. Then I have another model, and I predict these. I have like 2 models, take an average. I can also generate, as I'm pressing buttons, you can see that it just generates my results. You see that? So this is a very, just like a kind of industrial kind of a thing. You want to predict sports. You want to predict the stock market, Bitcoin, whatever it is you want to do. Feel free to pick something like that. But the requirement, you should use PyTorch, possibly a deep neural network. Can be classification or regression is fine. Images, whatever you want to do. Any questions? I'll show you guys the one thing here. So in this repo, I have, let's go back to here. let's go back here. Repo. Oh, it's actually I need to provide a new link. I'll give this link in the homework. Deploy to web. I think I have some examples here. Right, it's this, right? So these are examples. So this is wine quality. Pretty simple. Just picks a value. This one is kind of nice. Some students did this one. You can look at this code, right, as reference. And they would load an image, and it would predict what it was. I think they did something like panda, not a panda. So I have an image. That's a thumbnail, though. Let's see. I have a. I don't remember if it's JPEG or PNG. Let's just try it out. So I'll use this one because it loaded. Inference complete. Probability is not a panda, right? That's what it said. Because it's the highest. That book is definitely not a panda. All right. Let me. That was a picture of me. Let's see if it thinks I'm a panda. Not a panda. Different. And 92% certainty, right? So there you go. So you can do images. Actually, some students in the past used the camera because you can, from JavaScript, grab your actual camera, and then they did sign language. You know, they did like the symbols, and it would say sign language. Students have done. There's a thing in JavaScript where you can actually like write a number. Like you can write a 7 in a specific type of a widget that you put in. So you could use that as your input. Whatever you want, right? So I'm leaving it to your creativity. It could be as simple as regression, classification, but it'll be the requirement that you need to use PyTorch, ONNX, and some kind of deep neural network. Does that make sense, guys? As far as the homework, you've got everything you need at this point. Are there any questions about this homework? All right, so let me then go ahead and assign it to you guys, and so that I can then move on to the, once that's assigned, we can start talking about project and phase 1 of the project, which still uses PyTorch. So you're still in the same space, but this is going to be more of a competition. And I think I said, oh, by the way, you can do this project in groups of 2. Is that okay? Groups of 2. So the homework is obviously individual, but the project you can work not, you know, that's, I think that's a good number for both phase 1 and phase 2. All right. All right. So let's go ahead and create the homework assignment. Let's go back to the table of contents. So I'll do it here. Actually, here, I'll do it here. So I'll create an assignment link, new assignment. This battery's running low. Yeah. All right, so I'm going to call this one Torch and ONNX homework. Okay. Homework. It'll be implement and deploy a deep neural network model. Okay? As described in class, you must use PyTorch, ONNX, and deep learning. You can deploy your model using HTML, JavaScript, and GitHub pages. This is an open-ended assignment, so you can select either classification or regression. You can use files, direct inputs. I should say you can use files such as images or direct inputs like in a regression problem. Please use different data sets from the ones already used in previous labs or lectures. All right, is that clear enough, guys, as far as this assignment? Do you want some clarification? All right, so let's look at the calendar. I'm assigning it now, so you have from now until, today's the 30th, right? So how about, you guys are Monday, Wednesday, so the 15th. So it's going to be due on the 15th by 10 p.m. Got about 2 weeks, so that's a good amount of time, I think. And it'll open now, and it'll stay open until the 19th. Got it? All right, so that's your last homework assignment for the semester. And then the rest of the time you can focus just on phase 1 and phase 2 of the project. All right, that's table of contents. All right, so we completed PyTorch as far as, and I've assigned this, so that's pretty good. I'm not hearing any questions about this, so I'm assuming we can move on then. Okay, right? All right, great. So no questions. All right, perfect. So the next thing that we need to start talking about is then the term project. The way I think I've explained to you the reasoning behind it, right? So I break it up into 2 phases because in one phase you train the model from scratch. The weights are starting at random, and so you want to see how you can build a most amazing neural network, right, in PyTorch to train a model that just gets the best performance. And then we're going to do the competition, and you do the presentation and show your results. The second phase is where you will use something called transfer learning. And in transfer learning, you actually can borrow someone else's pre-trained weights. But you're also learning there that you're bringing in bigger models. It requires more GPU, so although you have all this power, you also have more problems in dealing with something that's much bigger. All right, so, but essentially you need to know also how to do transfer learning if you want to be competitive out there, because everyone is using it. If you show up and just do the from scratch approach, you will, in an image classification problem, you'll be beaten without a doubt, because you have to use the transfer learning approach. where you borrow someone else's weights and then you fine tune on your own data set. Do you guys see that? So that'll be phase 1 and phase 2. Okay, so next week on Monday, we will cover transfer learning. We'll get into that now, and we'll just start with very basic things like the PyTorch hub, okay? That will allow us to bring something called a ResNet 50, and you will learn how to do that part. We also have to learn one algorithm that's complicated called the CNN, and you will learn that also on Monday, okay? Makes sense? So we'll start transfer learning on then, but we are now done with this section of PyTorch, just how to build. You are at this point know how to build just a deep neural network. 2 layers, 3 layers, 20 layers, you can do it, right? And so we'll learn next week more of the idea of borrowing someone else's weights. It's very nice, but I get a little bit stressed with this part because the models are bigger. So usually my examples might be a ResNet 8, but if you guys want to win, go with a ResNet 50 and just figure out all the managing of memory and all that, right? That's why also we have Colab. Colab has GPUs and so on. So GPUs become much more important. Any questions for me, guys? No questions? All right, so I think this is, actually I had one more thing, so I do have 10 minutes. If you remember, this is now no longer PyTorch, right? So this is just, this class is about not just neural networks, obviously. It's about all the other algorithms, KNN, decision trees, and so on. So there is one powerful algorithm out there, and let me close this, called XGBoost. So I want to cover that one just briefly. So let's go back to this one. Since I have the data set here, and today we're talking about regression. So you just have it. So let's click on the repo. So wait, give it a minute. All right, so we come here to the link, and I'm going to click on, I clicked on that. Nope, that's not it. Let's click on this one, XGBoost. All right, and so we did all of this, the neural network, we trained, we also covered ONNX already. Here, right? So we just covered ONNX, but now we're going to switch gears from deep learning, and we still have the same wine quality data set. It's a regression problem, but I want to show you that there's this really nice, very powerful algorithm called XGBoost that you should have in your toolbox, and as you can see, it's pretty easy also. All right, so what do? First of all, we already, at the very top, right, if you imported the library, XGBoost. So here, I'm just going to call XGB, right, it's the library. I'm going to have to go all the way up. Right, so we imported XGBoost as XGB. So we use this library. It's very similar to sklearn. So it has that same vibe, but it's its own library. Okay, so xgb.xregressor, you essentially just use these default parameters, the number of estimators, some gamma parameter, max depth of the tree. All right, so we instantiated XGBoost now. And then obviously this one does not require PyTorch, so I'm actually just going to revert back to my original X-train, Y-train before we converted them into, so these are the, before they were converted into PyTorch. So we fit means train with the X train, Y train. You can see we got the green check. It's train. That's it. So that's it. So you just have now a nice train little decision tree, very much in the fashion of sklearn, and now you can predict. Do you see that? And so xregressor.predict. What do we predict on? The X test, of course. Gives us Y pred. We're going to compare this Y pred to what? Y real, right? And we're going to, because it's a regression problem, we measure it with R squared. So notice there's the data if you want to look at it. But now I do the R square. So Y test compared to Y pred, right? The exact same thing. Let's run it. 0.39. What was the value for the deep neural network? Do you guys remember? 0.33. Linear regression was 0.27. Deep learning was 0.33. This is 0.39. XGBoost, a little decision tree, very powerful. And I would always say neural networks are the best, but always have your XGBoost just in case, especially for this type of problem, a regression problem. Once the data gets massive architectures, yeah, neural networks. So it's like neural networks are really valuable when you have massive things. But in a very tiny regression type data set, this one is still pretty powerful. All right, guys, so excellent. So we finished up the regression discussion today. We looked at PyTorch and neural nets. We looked at XGBoost. And we looked at how to do ONNX. And I've given you your homework assignment. So you can go ahead. It's very open-ended, so you can pick a project as difficult, a homework as difficult as you want or as easy as you want. It's entirely up to you, but make sure you deploy it. All right? Please, we'll stop here for today. Reminder, on Wednesday you have exam 2, which we'll cover until now, right? And then also next Monday, we will start transfer learning and those ideas, all right? Still with PyTorch. All right, guys, I'll stay for a few minutes if you guys have questions.